So let's talk about the series and parallel combination of capacitors. Let's talk about series combination first. Let's suppose three capacitors are connected in series. Okay. So C1, C2, C3 are their capacitances and they are connected to each other, and other end of C1 is connected to a battery and other end of C3 is also connected to a battery. So a battery is, we can say, it's a collection of charges. Okay, a cell is basically collection of charges. Okay, for our purpose. So it will have two terminals. One is positive terminal and the other one is the negative terminal. So this is suppose positive terminal. This one is negative terminal. This is a battery. Okay. So because of that, there will be some potential difference. There will be some potential difference across the cell. Okay, and the potential difference is suppose V. Now if we connect these capacitors to this cell, what will happen? So we are connecting them by means of metal wires. Okay, so what will happen? So see, initially our capacitors are uncharged. Okay, our parallel plate capacitors are uncharged. Now what happens is, see, this end of this metal plate, it is connected to this end of the battery. So here we have a lot of positive charge. So what will it do? It will attract some electrons from here, right? It will attract some electrons from here, and those electrons, they will get deposited on this terminal. Okay, we can say they will move through the cell, and okay, they will emerge out of this negative terminal and they will move here. So let's suppose small charge delta Q, okay, minus delta Q, it came out of this terminal, it moved through this cell and it gets deposited on this plate of this capacitor C3. Okay, so what will be charged over here? So minus delta Q is moving like this. Okay, so you have removed charge equal to minus delta Q from this plate, otherwise the plate was neutral. So because you have removed the charge minus delta Q, the charge remaining there will be plus delta Q. Okay, and charge which gets deposited here, it's minus delta Q, right? Okay, so what will happen? So imagine here we have electrons. Okay, here we have negative charge. So negative charge gets repelled, right? Negative charge will get repelled from here. So let's suppose minus delta Q charge, it goes from here to this plate. So this plate will have charge equal to minus delta Q, and this plate will have charge equal to what? Plus delta Q. Okay. So now what will happen after that? So this plate has become negatively charged. So again it will repel electrons from here. So those electrons, they will get pushed towards this plate. So again this plate will have charge equal to minus delta Q and this plate will have charge equal to plus delta Q. Okay. So now if we see, the charge on all these plates of all the capacitors will be equal. Okay, plus minus delta Q. So this thing keeps on happening. This thing keeps on happening. Till what time? Till what time will it keep on happening? Till what time the electrons will keep on flowing towards this positive plate? Till the time potential of this plate and potential of this terminal of battery, it becomes equal. Okay, or we can say potential difference between this plate and this plate, right? This is our circuit. So potential difference between this plate and this plate, till it becomes equal to the potential difference across the battery. Till that time the electrons will keep on moving like this. Okay, from this terminal, sorry, this plate of C1 to this plate of C3, and then they will induce some charge, keep on inducing the charge. Okay, on this plate to this plate to this plate to this. And this is how the capacitors get charged when we connect them to the external battery. Okay. So let's suppose the final charge on them is plus q minus q plus q minus q plus q and minus q. Okay. So when charge is equal to this much, the potential difference across this plate of C1 and this plate of C3 becomes equal to the potential difference across the terminals of battery, positive and negative terminals of battery. So got it? Yes, no? Now what we are interested in. Okay, this is understanding of charging phenomena. Okay. Now what we are interested in is the effective capacitance of these three capacitors connected in series. Okay. So now see, we have seen this, that potential difference between these two plates will be equal to what? Potential difference across the battery. But there will be some potential difference across two plates of this capacitor, across two plates of this capacitor, and across two plates of this capacitor, right? So those potential differences are, suppose, V1, V2 and V3. Okay, these are potential differences across these two plates of C1, we can say these two plates of C2 and two plates of C3. Okay, so now the total potential difference between this this plate and this plate is V, and potential difference across these two plates is V1, across these two plates is V2, across these two plates is V3. So I can say V is equal to V1 plus V2 plus V3, right? Okay, so I'm going to write this down. So suppose now what has happened, so capacitors are charged, okay, to charge q, suppose, okay, then, or we can say capacitors are fully charged, okay, then V will be equal to what? V1 plus V2 plus V3. And now what will happen? Now there will be no more flowing of charges. Okay, now electrons will not move. Okay, or we can say in other words that there will be no flow of current because capacitors are fully charged. Okay, so V is equal to V1 plus V2 plus V3, and then we know what is capacitance. It is charge upon potential difference. Okay, so this is series combination. So let's suppose Cs is the capacitance of, let's suppose Cs is capacitance, effective capacitance of the series combination. Effective capacitance of the series combination. Okay. So we know that capacitance is equal to charge divided by potential difference. So for this series combination, we can say the capacitance is measured across these two plates, between these two plates, right? These are extreme plates, so it is capacitance between those two extreme plates. So how much is charge if we consider this complete thing as one capacitor? So how much is charge on its positive plate and negative plate? So charge is q. And how much is potential difference? Potential difference is equal to V, right? And therefore I can say if effective capacitance is equal to Cs, then it is equal to q divided by V, right? And therefore we can write that V is equal to, from this, okay, if we take V on this side, Cs on the other side, we get V is equal to q divided by Cs, okay, and then we can put it over here. Okay, so similarly we can say V1 will be equal to what? So V is equal to q upon charge upon capacitance. So V1 will be equal to charge on this capacitor divided by its capacitance. V2 is equal to charge on this capacitor divided by its capacitance, and V3 is equal to charge on this capacitor divided by its capacitance. Okay, so we can say that therefore Q divided by Cs is equal to Q upon C1 plus Q upon C2 plus Q upon C3, and Q we can take it common and cancel it out. So we get 1 upon Cs is equal to 1 upon C1 plus 1 upon C2 plus 1 divided by C3. So it means that if we connect 3 capacitors in series, then the effective capacitor is given by this formula. 1 upon Cs is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Okay. And similarly, if we connect n capacitors, we'll get for n capacitors, we can write 1 upon Cs is equal to 1 upon C1 plus 1 upon C2 plus so on and so forth up to plus 1 upon Cn. Right. So this is the formula for effective capacitance in series combination. Is it clear? Okay. So now we'll just remember one specific case of this, and that is when we connect only two capacitors. Okay. Then what happens? So for two capacitors, we can write 1 upon Cs is equal to 1 upon C1 plus 1 upon C2. Okay. And therefore we can write 1 upon Cs is equal to, we have to make denominator of this thing same. So first term will multiply by C2 and second term will multiply by C1. So it is C2 plus C1 divided by C1 C2, right? This is what we will get. And if we take its reciprocal, we get Cs is equal to C1 C2 divided by C1 plus C2. Okay. So if we have just two capacitors, we can memorize this simple formula. The net capacitance is equal to C1 C2 divided by C1 plus C2. Let us see capacitance in parallel combination. Okay. So parallel combination of capacitors. Alright. So now we have some capacitors connected in parallel combination. So let's suppose this is C1, this is C2, this is C3, and they are connected in parallel combination. So we have three capacitors now, and they are connected to this battery whose potential difference is V. So this is positive terminal, this is negative terminal. Now what will happen? So initially all three capacitors are uncharged. All three capacitors are uncharged. Okay. So now we can say that since all of them are uncharged, potential at this terminal is 0. Okay. Then this terminal is at some negative potential. So what will happen? The negative charge will flow towards this these plates, right? So let's suppose some negative charge flows from here. Okay, it approaches this terminal. What happens here? The charge gets divided into two paths. Okay, some charge will flow here, some charge will flow along this path. Then that remaining charge, it will come here. Okay, again it gets divided along two paths. So some charge will flow here, some charge will flow towards the next capacitor, right? So this is suppose C1, C2, C3. So now what will happen? Ultimately, So charge will keep on flowing till the time potential difference across the two plates of all capacitors is equal to potential difference across the battery. Okay, because see, all of them are connected to same battery. Okay, see, all of these capacitors, they are connected to same battery. So the negative terminal, we can say, negative plate is connected to negative terminal of battery, and positive plate, or we can say one plate is connected to the positive terminal and one plate is connected to negative terminal. Okay, so it happens so that the plate which is connected to negative terminal, it will acquire some negative charge, and then the electrons from this plate, they will get repelled. Okay, they will get repelled and they will enter the battery, positive terminal of battery. So that's why the other plate will become positively charged, right? So what happens is, now depending upon their capacitance, the capacity of them to store a charge at a particular potential is different, right? Because C is equal to what? Q upon V. So V is same for them, but capacitance is different. So charge on each of them will be different, right? Charge on each of them will be different. Okay. So let's suppose charge on the first capacitor is Q1. So this is plus Q1 minus Q1. This is plus Q2 minus Q2. Charge on second capacitor. And charge on third capacitor is plus Q3 minus Q3. Okay. And suppose now they are fully charged to their maximum capacity. We want to find out the equivalent capacitance of the parallel combination. So if we collect these three capacitors, the total charge on them, we can say is Q1 plus Q2 plus Q3. Okay, if we think of, see, all these three capacitors, they are connected. So to this point and this point, we can say. Okay, so this point, the charge on this point, okay, the total charge on the three plates connected to this point, it is Q1 plus Q2 plus Q3, and total charge which is on the three plates which are connected to this point is minus Q1 plus minus Q2 plus minus Q3. So the capacitance that we will measure is between these 2 points now, because these 2 points are connected to these 2 terminals of battery. Okay, so this is the effective capacitor. So charge on effective capacitor is Q1 plus Q2 plus Q3, right? Okay, so in parallel combination, so total charge Q is equal to Q1 plus Q2 plus Q3. Okay, and suppose Cp is the effective capacitance. Cp is the effective capacitance. Then we can say, since capacitance is equal to charge divided by potential difference is same for all of them. So we can say charge is equal to C multiplied by potential difference. Okay, C is equal to Q divided by V. So Q is equal to C multiplied by V. Okay, so it is Cp times V. So we can put that here. So what will be Q1? Q1 is equal to C1 multiplied by potential difference across two terminals of this capacitor. C2 is equal to Q2 is equal to C2 multiplied by potential difference across these two terminals. Okay, and Q3 is equal to C3 multiplied by potential difference across these terminals, okay, of this capacitor. The potential differences are equal, right? So therefore what we get is, we get Cp times V is equal to Q1, which is C1 times V plus Q2, which is C2 times V, plus Q3, which is C3 times V. And we can take V common here and we can cancel it out. So we get Cp equals to C1 plus C2 plus C3. Okay. So if we have three capacitors, the net capacitance of parallel combination is C1 plus C2 plus C3. If we have n capacitors, it will be C1 plus C2 plus C3, so on and so forth up to Cn. Now we'll see some problems based upon what we discussed yesterday and what we discussed now. Two metallic spheres of radii 1 centimeter and 3 centimeter are given charges of -1 multiplied by 10 raised to -2 coulomb and 5 multiplied by 10 raised to -2 coulomb respectively. If these are connected by a conducting wire, the final charge on bigger sphere is. So we have two metallic spheres, R1 and R2 is given and charges on them are given. So let's suppose this is sphere 1, this is sphere 2, and we connect them by means of a wire. So this is some wire. Okay, what will happen now? So initially charge on the first one was Q1, charge on second one was Q2. Their radii were R1 and R2. If we connect them by means of this wire, what will happen? Initially there could be some potential. Okay, so this one was at potential V1, this one was at potential V2, we can say, and that potential is 1 upon 4 pi epsilon naught Q1 upon R1, and for this one it is 1 upon 4 pi epsilon naught Q2 upon R2, right? But when you connect them by means of a wire, then the charge will flow from first to second or from second to first, and the potential difference across so till the time the potential difference becomes zero. Okay, so ultimately we can say the potential on both of them will be equal, right? So see, so we can say initially, okay, initially charge on them was Q1 plus Q2, okay, so the total charge, so which is equal to -1 multiplied by 10 raised to -2 plus 5 multiplied by 10 raised to -2, and that is 4 multiplied by 10 raised to -2. Okay, so total charge is equal to 4 multiplied by 10 raised to -2 coulombs, right? Then after you connect wire, so final charge will also remain same. Final charge will remain same. So charge is not going anywhere. So final charge is also equal to Q. So total charge is Q. Final charge is also equal to Q, but there will be redistribution of charge. So this is suppose I'm sorry, Q1 dash and Q2 dash are their final charges. Okay, so Q is equal to Q1 dash plus Q2 dash, right? But again, what will happen? So the potentials on them will become equal. Okay, till that time the charge will keep on moving. So we can say 1 upon 4 pi epsilon naught, or let's call it K only. So K multiplied by Q1 upon R1 is equal to K multiplied by Q2 divided by R2. Okay, Q1 dash, Q2 dash. This is the final charge, right? Q1 dash and Q2 dash. So K and K will get cancelled, and we want final charge on bigger sphere. So let's write Q1 dash equals to, so Q1 dash equals to what? R1 upon R2 multiplied by Q2 dash. Okay, and now what we can do? We can put this over here. So what we get? We get that Q1 dash is equal to R1 upon R2 multiplied by Q2 dash. So R1 upon R2 multiplied by Q2 dash plus Q2 dash is equal to Q. And what is Q? What was the total charge? 4 multiplied by 10 raised to minus 2. It is 4 multiplied by 10 raised to minus 2. Right. So we can say, what is R1 and R2? R1 is 1 centimeter. R2 is 3 centimeter. So R1 upon R2 is 1 divided by 3. So 1 upon 3 Q2 dash plus Q2 dash is equal to this thing, 4 multiplied by 10 raised to minus 2. So this is 1 upon 3 plus 1. That means 4 upon 3 is 4 multiplied by 10 raised to minus 2. Okay, so 4 upon 3, okay, Q2 dash is equal to 4 multiplied by 10 raised to minus 2. So this 4 gets cancelled. So Q2 dash is 3 multiplied by 10 raised to minus 2 coulombs. Okay, this is the answer. Got it? Yes, no? The electrostatic force between the metal plates of an isolated parallel plate capacitor C having charge Q and area A is. So we have parallel plate capacitor and charge on that capacitor is Q, area is A. So force between metal plates. Okay. Option A is independent of the distance between the plates. Option B, linearly proportional to the distance between the plates. Option C, proportional to the square root of the distance between plates, inversely proportional to the distance between the plates. Okay, let us solve this. So question is force between the plates. Does it depend on distance or does it not depend on distance? Only distance, right? Okay, so this is, suppose, first plate of capacitor. This is second plate of capacitor. So how to find force between these two? So charge on them will be plus Q and minus Q, right? So we can say that, okay, we can think this way, that one plate is kept in the electric field of the other plate, right? One plate is kept in the electric field of other plate. So we can say that negative plate, suppose, for an example, is kept in electric field positive, or vice versa. You can say positive plate is kept in electric field of negative. The same thing. Okay. So how much is electric field produced by this one? This positive plate at this point, sigma divided by 2 epsilon naught, right? So E due to positive plate is sigma upon 2 epsilon naught, and therefore force on negative plate F is equal to EP multiplied by the charge on that plate, which is minus Q. Okay, so F is equal to EP is sigma upon 2 epsilon naught multiplied by minus Q. And what is sigma? Sigma is charge upon surface area, because area is given in this problem. Okay, it is Q upon area. So force will be equal to minus Q square divided by 2A epsilon naught. Okay, so it depends on charge, it depends on area, it depends on epsilon naught. Does it depend on distance? It does not depend on distance, right? So option A is the answer, independent of distance between the plates. Parallel plate air capacitor has capacity C, distance of separation between plates is D, and potential difference V is applied between the plates. Force of attraction between plates of parallel plate air capacitor is. So force we have just calculated. Where is it? Q square upon 2A epsilon naught, if we just consider the magnitude. Okay, it has to be calculated like this, right? So force is asked. So F is equal to force between two plates of capacitor is Q square divided by 2a epsilon naught, and we want it in terms of C, V and D. Okay, so we can write, so sigma is equal to, not sigma, we want C, right? Okay, so C is equal to Q upon V, Q is equal to CV. We can use this thing, make use of this thing. Q is equal to CV. So what do we get? We get C square V square, because we have Q square. It's 2a epsilon naught. Okay, still doesn't make it. Okay, then we have a and epsilon naught. So we know formula of capacitance in terms of epsilon naught a. Capacitance is epsilon naught a divided by d. We can put it there. So epsilon naught a is equal to CD. C square V square divided by 2 CD. Okay, so this C and this C will get cancelled. So we got CV square divided by 2D. This is the formula for force. Okay, so option A, not A, option D. Option D. Let's read the problem. A parallel plate air capacitor is charged to a potential difference of V volts. After disconnecting the charging battery, the distance between plates of the capacitor is increased. Okay, it is charged and then you increase the distance between plates using an insulating handle. Okay, as a result of the potential difference between the plates increases, decreases, does not change, becomes zero. Can you say? Can you tell? This one is simpler, right? You have charged a capacitor. So what will happen? There will be some electric field. What is electric field? Sigma divided by epsilon naught, right? Electric field between two plates of capacitor. Okay, sigma upon epsilon naught, and it is constant from first plate to second plate within that region. Okay, it's sigma upon epsilon naught. Then we know electric field is potential difference. Okay, delta V, potential difference we can say. We are writing it as V for capacitor only. Okay, but V is potential difference between plates, right? So potential difference divided by D. Okay, it's potential difference divided by D. So you take that D on other side, so we get V equals to E times D. So once you have charged a capacitor, the charge will remain same. So sigma will remain same. So it is epsilon naught, sigma upon epsilon naught multiplied by D. So if you are increasing the distance between plates, what will happen? Potential difference will increase. Okay, so it's option A. Right. It's option A. Good. Three capacitors each of capacitance C and of breakdown voltage V. So breakdown voltage is basically the maximum voltage that you can apply between two plates of capacitor. If you increase the voltage beyond that, what happens is the air gets ionized and the charge will flow from one plate to the other plate, right? So you can apply some potential difference. See, when you charge a capacitor, there will be some positive charge here, negative charge here, sorry, negative charge here, and if you keep on increasing the charge, what will happen? So air has molecules, right? Atoms or molecules, mostly they are molecules. Okay, H2, O2, N2, etc., etc. Basically it's okay, O2 and H2. Okay, so these molecules will get ionized, right? Okay, if you increase the electric field too much, right? So if you charge a capacitor too much, okay, beyond a particular potential difference, then what will happen? The air between these two plates will get ionized and the charge will flow like this. So these electrons, they will flow through the air between the two plates. Okay, and that means these two terminals or two plates are shorted now. So what will happen? The charge will get nullified. Got it? Yes, no? Okay, charges will flow through the air. Okay, and if you want to see, there are lots of demos on YouTube also, or if you have some science center near you, you can check it there. Okay, all right. So lightning also is one such example. Okay, when potential difference becomes too much, the electric field between clouds and earth, we can say, becomes too much. Okay, the potential difference becomes greater than the ionizing potential of the air, the medium. Then what happens? The air becomes ionized and charges flow. Okay, from cloud to earth, we can say positive charge, or from earth to the clouds, negative charge. Right. All right. So breakdown voltage is maximum voltage that we can apply. So then three capacitors, each of capacitance C and of breakdown voltage V, are joined in series. They are joined in series. Capacitance and breakdown voltage of the combination will be. So this is simplest question. Series combination, three capacitors, what will happen? So net capacitance is 1 upon Cs, which will be equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Okay, and C1 is equal to C2 is equal to C3. So it will be 1 upon C plus 1 upon C plus 1 upon C. That means 3 upon C is 1 upon Cs. Okay, and therefore Cs is equal to C divided by 3, right? Okay, so actually there is one more point to remember here. If you have identical capacitors connected in series, identical and capacitors connected in series, so equivalent capacitance will be equal to C divided by N. Okay, if they are connected in parallel, then equivalent capacitance Cp will be equal to N times C. Okay, this is one more point to remember. Okay, this is simple actually. This is like common sense. Okay, all right. So total capacitance here will be, because these are three equivalent capacitors connected in series. So equivalent will be C divided by 3. And what about the potential difference? So potential difference in series gets added. Okay, so for first one it is V, for second one it's V, for third one it's V. So it's V plus V plus V, 3V. Okay, so it's option B. Network of 4 capacitors of capacity equal to C1 equal to C, C2 equals to 2C, C3 equal to 3C, and C4 equal to 4C are connected to a battery as shown in the figure. Ratio of charges on C2 and C4 is, okay, charges on C2 and C4 is what we are asked. All right. So potential, okay. So what will be total capacitance here? What will be total capacitance of these three? So they are connected in series. C1, C2 and C3 are connected in series. Okay. So we can say 1 upon Cs for these three. Okay. For these three. 1 upon Cs is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Right. So then it's like these three are connected in series. So this is Cs, and then C4 is connected in parallel of that. Okay, and they are connected to this battery. So 1 upon C1, it's 1 upon C plus 1 upon 2C plus 1 upon 3C. We have to make its denominator same. LCM will be 6. So it is 6 upon, okay, it is 6C, right? 6 divided by C. So this thing we have to multiply by 3 and this one by 2. Okay, so it is 6 plus 3 plus 2 divided by 6C. This is 1 upon CS. What will be CS? CS is equal to 6 plus, 6C divided by 6 plus 3 plus 2, 11. Okay, how much is C4? C4 is equal to 4C. C4 is equal to 4C. Okay, now they are connected in parallel combination. So charge on this one is suppose QS, and same will be charged on all three of the series combination, right? Okay, so we have to find QS. We have to find out QS. So QS we can say, so C is equal to Q upon V, Q equals to CV, CS times V, and Q4 is equal to C4 times V because they are in parallel combination. Okay, the ratio of C2 to C4. That means, sorry, we don't want charges. Yeah, we want charges, right? We want ratio of charges. C2 to C4. That is, we want QS to Q4. So it is C, okay, QS Q4 is just equal to CS divided by C4, and that is 6C upon 11 divided by C4. C4 is how much? 4C. So C and C gets cancelled. So this is 6 by 4 or 3 by 2 we can say. It is 3 divided by 22. Yeah, 3 divided by 22. This is the answer. Option B. Three capacitors, each of capacity 4 microfarad, are to be connected in such a way that effective capacitance is 6 microfarad. This can be done by, you have three capacitors of 4 microfarad and they have to be connected in such a way that the effective capacitance is 6 microfarad. So how can you do that? So you don't have any choice, but you have to do trial and error in this kind of a question. Okay, this is first capacitor, this is second capacitor, let's suppose. So this is 4, and this is 4. So if you connect them in parallel, what will happen? It is 4 plus 4, 8 plus 4. This will not work, right? So total will be 12 microfarad. Okay, if you connect like this. If you connect two in series, one in parallel with that series, will this work? Let's check. So this is 4, 4, 4. So this series, two capacitors in series, the equivalent will be C by 2, right? Identical capacitors. So this thing will give us 4 by 2. Okay, C by 2 or 4 is equal to 4 by 2, 2, and this is 4. Okay, so it is 2 and 4 in parallel, so it will be 6. Okay, so we want 6. So this thing will give. Okay, so is there such an option, connecting two in series and one in parallel? Right, option C is the answer. Next question. Capacitor of capacity C1 is charged up to V volt and then connected in parallel to an uncharged capacitor of capacity C2. Final potential difference across each will be. Okay, so you have first capacitor which is charged. second is uncharged. So this is first one, capacitance is C1, charge on it is Q1. Second one has capacitance C2, it is connected in parallel. So initially it is not charged. Initially it is not charged. So now what will happen? So this charge will get distributed, right? So total initial charge is Q1 is equal to Q1. And now suppose final charges on them are Q1 dash and Q2 dash. Final charges on them are Q1 dash and Q2 dash. So there was no charge on this capacitor. Okay, only this one was charged. So we can say this sum of this charge will get distributed. Okay, it will get transferred to C2, right? So Q1 will decrease, but the total will remain same. So I can say Q1 is equal to Q1 dash plus Q2 dash. So Q1 we can write as C1 times V, because this one is charged, potential V. Q1 dash. Now suppose because they are connected in parallel combination, okay, potential across both of them will be, potential difference across both of them will be equal. So let's suppose potential difference is V dash, okay, and potential difference is V dash between these 2 points, V dash. So Q1 dash will be equal to C1 multiplied by V dash, Q2 dash is equal to C2 multiplied by V dash. We want to find out common potential difference, so we can take it common, okay. So we'll be left with C1 plus C2. We can move it on other side. So what do we get? I'm sorry, V dash is equal to C1 upon C1 plus C2 multiplied by V, right? It's option B. What is the effective capacitance between points X and Y? Okay, so this combination, it is known as Wheatstone Bridge combination. So it will appear in capacitors, and more often it will appear in electricity, current electricity, the next chapter that we will see. Okay, so see this combination, and this question, this kind of question, I mean, it has been repeated. Okay, so see, how is this Wheatstone bridge combination? So we have this point X, this point Y. Okay, we have these 2 points C and B. So this B is connected. Okay, this B is connected. So you can stretch B like this, and you can stretch C. So what will happen if you stretch them? Okay, you will get top point and a bottom point of Wheatstone bridge network that I'm going to draw now. You have this point X, okay, which is connected to this point A, right? So C1 equals to 6 microfarad. Okay, after that you have this point B, right? This point is B, this point is A, and there is another capacitor connected to point A, which goes till point C. So this is your point C. Now there is capacitor connected between C and B. Okay, so let's draw that. There is a capacitor connected between C and B. And after that, from point B, you have connected another capacitor to point D. So from point B, I have connected another capacitor to point D. Another capacitor to point D, and D I am connecting to this point Y. Okay, and between C and D, see, between C and D, you have connected another capacitor. Okay, so between C and D, you have connected another capacitor. Okay, so this thing will look like this. Okay, so what is capacitance between B and C? It is 20 microfarad. This is 20 microfarad. Okay, which one? This one. Between B and D, 6 microfarad. All others are 6 microfarad. All others are 6 microfarads. Okay, so you got it in this point. So this type of a network, it is known as Wheatstone's bridge network. Okay, so now we'll not go into that. But see, now once you charge them, let's suppose you start charging. Okay, you connect this across a battery. So what will happen? Point A will be at potential equal to positive terminal of the battery. Then there will be some potential drop. There will be some potential drop. Okay, so point B will be at some potential, and that potential is given by what? It is given by C. C is equal to Q upon V, and this capacitance is equal, right? So they will get charged to equal capacity. Okay, so charge on this one and this one will be equal. So we can say potential difference between these 2 points and potential difference between these 2 points will be equal. Okay, so B and C will be at same potential. B and C will be at same potential. Okay, so now if they are at same potential, no current will flow, no charge will flow between B and C. No charge will flow from B and C, between B and C, right? So there is no flow of charge. So this thing, this capacitor, okay, whether it's there or it's not there, it is not going to get charged. Got it? Okay. So for that to happen, what needs to happen is the ratio of these two capacitors. Okay, now these are equal, but in general, ratio of these two and these two should be equal. So let's call them C1, C2, C3, C4. So if C1 upon C2 is equal to C3 divided by C4, okay, this is known as balanced bridge. So the B and C, they will be at same potential. Got it? So no charge flows between them. We can remove that capacitance. Okay, and therefore now we have just these two capacitors connected here and these two capacitors connected. Right? So our network becomes simplified. So all of them are 6, 6, 6, 6. I'm sorry. So these are in series. What will be net capacitance? 6 divided by 2. It is 3. And this is also 6 upon 2, 3. So 3 and 3 in parallel. What will be net capacitance? It will be 6. Right? 2 times 3. So net capacitance is 6 microfarad. Option D. So let's move on to next question. In a parallel plate capacitor, the capacity increases if area of the plate is decreased, distance between plates increases, area of plate increased, dielectric constant decrease. So tell me, capacity increases. So let's just write down the formula. C is equal to, since there is dielectric also, epsilon naught Ka divided by D, and we want capacity to increase. So area is decreased, no, then capacity will also decrease. Distance is increased, again, if denominator is increased, capacity will decrease. Area is increased, yes, area is increased, capacitance will increase. So it is option C. Dielectric constant decreases. So yeah, if dielectric constant decreases, what will happen? Again, capacitance will decrease, right? So it is option C only. Capacitance of two concentric spherical shells of radii R1 and R2. R2 is greater than R1 is. So this is direct question. We had derived this formula yesterday, so you have to memorize it. Okay, this is the answer. Direct question. Okay, suppose you get confused between this one and this one, so we can check it using dimensions. Okay, that's what I'm saying. So capacitance of a single capacitor, spherical capacitor, is 4 pi epsilon naught R. Okay, now if you consider this option, so here in numerator you have R2 minus R1, so this is a distance, and R1 R2, so this is distance square, right? So distance divided by distance square will give you what? Distance in the denominator. Okay, so dimensions of this option becomes 4 pi epsilon naught, whatever the dimensions. Okay, whatever is dimension of epsilon naught, so 4 pi epsilon naught divided by L. But for capacitor it is 4 pi epsilon naught multiplied by L, not divided by L. That means this one is not the correct option. This one is correct. Spherical drop of capacitance 1 microfarad is broken into 8 drops of equal radius. Then capacitance of each small drop is. This is simple. Okay. So see, we have a spherical capacitor and it is broken into 8 drops. What will happen? Volume remains constant. So I can say volume of one big drop is equal to 8 times, because we are breaking it into 8 parts. 8 times volume of a small drop, right? So it is 4 by 3 pi r cube is equal to 8 times 4 by 3 pi small r cube. This is the volume of a sphere. 4 by 3 pi, 4 by 3 pi gets cancelled. So we get relation between capital R and small r. So if we take cube root, so cube root of 8 is 2. Capital R is equal to 2 times small r. Okay. So what will be ratio? So capacitance of small drop, C small divided by C of big, is equal to 4 pi epsilon naught small r divided by 4 pi epsilon naught capital R. So 4 pi epsilon naught cancelled to small r upon capital R. That's the ratio. Okay. So that is 1 by 2. Right. Small r divided by capital R is, if you take the 2 on other side, 1 by 2. So C small, I'm writing small. C small is equal to C big divided by 2. Okay, so it was 1 microfarad, it becomes half. Option A. When a capacitor is connected to a battery, what happens? Okay, option A, current flows in the circuit for some time, then decreases to 0. Option B, no current flows in the circuit at all. Option C, an alternating current flows in the circuit, and option D, none of the above. When capacitor is connected to battery, current will flow till the time it gets charged. After it gets charged, there is no flow of current. So it is option A. Current flows in the circuit for some time. Yeah. Then it decreases to 0. Right. It's option A. Cylindrical capacitor. A cylindrical capacitor has two coaxial cylinders of length. Actually, there was no question asked on the cylindrical capacitors. Okay. So, uh, not in NEET at least, or in similar exams. Anyways, so let's see this. A cylindrical capacitor has two coaxial cylinders of length 15 centimeter and radii. 1.5 and 1.4 centimeter. The outer cylinder is earth and the inner cylinder is given a charge of 3.5 microcoulomb. The capacitance of the system is, okay, the capacitance of cylindrical capacitor C is equal to, it's 2 pi epsilon naught, I guess, uh, multiplied by L divided by log of R2 upon R1. We want the capacitance only. All right. So yeah, then this is simple. We just have to substitute values here. Okay. So we know 1 upon 4 pi epsilon naught is equal to 9 multiplied by 10 raised to 9. So 2 pi epsilon naught will be, so 1 upon 2 pi epsilon naught will be 18 multiplied by 10 raised to 9. Okay, so 2 pi epsilon naught is 1 upon 18 multiplied by 10 raised to 9. Multiplied with length is 15 centimeters. 15 multiplied by 10 raised to minus 2, and log of R2 upon R1. So R2 is 1.5, R1 is 1.4, right? So it will be log of 1.5 divided by 1.4. Oh, we need log table here. Okay. Actually, we need log table. So yeah, you can check this. Okay. So this is how we will solve, right? It is direct question. We have to put values. That's it. We can get 10 raised to 9 in numerator. It will become 10 raised to minus 9. So 15 divided by 18 is 5 by 6 multiplied by 10 raised to minus 11 divided by, we have log of 1.5 divided by 1.4. Okay, this is natural log. Right. So we need log table here. So this will be close to 1.1 and it will be 2.303 multiplied by log to the base 10 of 1.1. Okay. What's that? I don't know. Maybe 0.99 something. Anyway, so is there an, okay, you can calculate it, right? Okay. A long hollow conducting cylinder is kept coaxially inside another long hollow conducting cylinder of larger radius. Both the cylinders are initially electrically neutral. Okay. Potential difference appears between the two cylinders when a charge density is given to inner cylinder. Potential difference appears between the two cylinders when charge density is given to inner cylinder. This is correct. Okay. No potential difference appears between two cylinders when a uniform line charge is kept along the axis of cylinders. Okay, this is wrong. I'm sorry. Potential difference appears between two cylinders when charge density is given to outer cylinder. This cannot happen. None of this. Okay. So let me explain these three options. Okay. So see, we have two cylinders like this, and we had discussed this yesterday. But suppose there is some charge on the inner cylinder. Now charge on outer cylinder is suppose Q2. So it will produce some potential. Okay. So potential on first cylinder V1 will be due to charge on itself plus charge on outer cylinder, and potential on Q2 also, it will be due to charge on inner cylinder and charge on outer cylinder. Okay. But what happens is when we find potential difference V1 minus V2, then the potential due to charge on outer cylinder gets cancelled out. This thing happens for cylinders, this thing happens for spheres also. Okay, potential on Q1 potential on first due to charge on Q2 and potential on Q2 due to charge on Q2, it is equal because potential on a hollow conductor and inside hollow conductor, it's equal. So potential due to charge on Q2 gets cancelled out. So basically potential is because of charge on Q1 only. Sorry, potential difference is because of charge on Q1 only. You got this? And that's why this option, no potential difference appears the between two cylinders when a uniform, not this one. Potential difference appears between two cylinders when charge density is given to outer cylinder. So if you give charge density to outer cylinder, nothing will happen because potential due to outer cylinder on inner cylinder and on outer cylinder is equal. Is it clear? If you give charge to inner cylinder, then only there will be potential difference. Okay, so this option is ruled out. But then this option B, no potential difference appears between two cylinders when a uniform line charge is kept along the axis. So they are claiming no potential difference appears. Okay, so charge is not given to any cylinder in this case, but what is done is you have kept a uniform line charge along the axis. So there is some charge on this one, Q. Okay, so since there is some charge, now it will create some potential on the inner cylinder and some potential on outer cylinder also. And since outer cylinder is at a larger distance, potential on it will be lesser. So this line charge will also create some potential difference, right? So this option is also not correct. Okay, this is not correct. This is not correct. If you charge this one, the inner cylinder, of course there will be some potential on inner cylinder and some potential on outer cylinder due to charge on inner one. But potential on inner one will be greater than potential on outer one due to charge on inner cylinder. So therefore there will be some potential difference. So this is correct. Potential difference appears between two cylinders when a charge density is given to inner cylinder.